Hi there, I'm Paul Belflem and this is Industrial Organization. In this presentation I want to show you how we model consumers in industrial organization. The learning objectives are the following. We are reviewing some microeconomic notions that will prove very important for industrial organization. Here we focus on utility and demand, on the welfare analysis of market outcomes, and on the consumer surplus. If you want some background reading, look at sections 213 and 214 in the textbook. Right, we start with the consumer's decision problem. I'm first going to present it in a very general way, and then I'll move to two specific examples. Okay, so think of a consumer choosing the quantities of several goods. Good 1, good 2, up to good n. To fix ideas, think of you, the consumer, choosing the quantities of different vegetables. Tomatoes, cabbage, zucchini, whatever. Okay, so this is really what we are looking at. We are looking for the market for vegetables here, and as I will explain later, we adopt what we call a partial equilibrium approach, which basically means that we look at one market at a time. Here, for this example, the market for vegetables. Okay, of course, as a consumer, when you choose vegetables, you know that you are going to choose other goods as well. You may want in the supermarket to choose chocolates, or think of buying a car or buying a fridge, right? Well, we don't look at the problem of the consumer in its all generality. We look at the market for vegetables. So it's as if we were putting all the other goods you could choose from within a kind of combined commodity, which is called a Hicksian composite commodity, and the quantity of this composite commodity is called Q0. Okay, so in a sense we decompose the problem of the consumer by assuming that the utility function of the consumer has this quasi-linear form. There is a utility made of the quantities of the goods that matter for this analysis, the vegetables, right? And you add to this utility the utility coming from the other goods, the composite commodity. Okay, and as you will see very quickly, we will somehow get rid of these other goods that do not really matter for the analysis. How do we do so? Well, as you know, the consumer is choosing the quantities to maximize its utility, but of course you're constrained by the budget you have, right? And how do you, this budget is Y, and it can be spent on the several goods you can acquire, the vegetables, this vector Q, which multiply by the price of the respective vegetables. Okay, so P is also a vector of prices. And then you have the spending coming from what you will pay for the composite good. And you see here that we have normalized the price of the composite good to 1. Okay, so it's also called the numéraire. Okay, so P times Q, that's the total spending on vegetables, plus Q0, the total spending on the composite good, or the other goods, if you want. Okay, and this total spending cannot be larger than your budget Y. Okay, well, as you're maximizing, you want to go up to the limit of your budget, so this constraint is going to hold with equality. Okay, and so in a sense, you can substitute, you can use this equality here to substitute Q0 for Y minus P of Q. So Y minus P times Q, sorry, this is what you haven't spent of your budget on your purchase of vegetables. Okay, and so using this equality here, Q0 is equal to Y minus P times Q, you can rewrite the maximization problem of the consumer as the following expression. You want to maximize the utility U of Q by choosing the quantities Q plus U of Q plus Y minus P of Q. Y minus P of Q is the utility you get from the composite good, after having included the budget constraint. Okay, now this is how you write the problem of the consumer, maximizing utility given the budget constraint. And if you, sorry about that, if you take the first order derivative for each of these quantities, Okay, the solution to these first order conditions will give you the individual demand functions. Okay, so the demand function for each good from a particular consumer. Now, as we want to analyze a particular market, here the market for vegetables, we want to aggregate the demand functions of the different consumers. And as we will see in the next two examples, there are two basic ways to do that. Either you would assume that there is one consumer who is representative of all the others. Think of a kind of average consumer, right? And so this consumer will actually be the demand, or the demand of this consumer, to say this in more correctly, the demand of this consumer will represent the demand of the whole market. Okay, that's one approach. Another approach is to consider the consumers are different from one another, but we will somehow aggregate their demand behaviors, for example, by adding up the quantities that each of these consumers wants to buy at a particular price. Again, I'm going to give you in a moment one example of this approach. Okay, so let's look at the first approach, which is the representative consumer approach. As I said, we will consider that all consumers can be summarized as one single consumer, whom we call the representative consumer. Okay, and here is an example of how we will derive the inverse demand functions and the demand functions starting from a particular utility function in following the steps that I gave you on the previous slides. Right, here is one particular utility function. There are two goods that the consumer is interested in. Let's say tomato, good 1, and cabbage, good 2. Okay, and this function here, well, the first part gives you the utility, and as we did before, we substitute for the composite good the budget constraint. So you see here minus P1Q1, that's the spending on tomatoes, minus P2Q2, that's the spending on cabbage, and Y is the total budget of the consumer. Okay, now if you want to get the inverse demand, you need to solve this problem for the choice of quantities. Mathematically, it means that you take the first order derivative of this function here with respect to Q1 and to Q2, and you equate this first order derivative to 0 in order to get the maximum. Okay, so this is what we have done here. Maximizing, well, sorry, deriving the function with respect to Q1 and equating this to 0 is equivalent to A minus B times Q1 minus D times Q2 should be equal to P1. Okay, and same thing here for the derivative with respect to Q2. Okay, so take some time to review this at your own pace. Later on, just freeze the screen and you can check if you understand this correctly. Okay, so here I just rewrite this as inverse demand functions. So why are they called inverse demands? Well, usually the demand expresses the quantity demanded as a function of the prices. Here we have the opposite. We've got the prices as a function of the quantities. Okay, so I want to pause here a little bit to explain the meaning of the different parameters in these functions. So first we have A. You can see A as the maximum price that the consumer is willing to pay for each good. Okay, now for a particular quantity, what the consumer is willing to pay will be lower than that. Okay, it will decrease with the own quantity of the goods with this parameter B. Okay, and it will decrease with the quantity of the other goods according to this parameter D. Okay, D plays an important role here because it will somehow indicate how close substitutes the two goods 1 and 2 are. Okay, so D, we assume, can take any value between 0 and B. And let's look at the two extreme cases. If D is equal to 0, then you can see that the third term here in the demand function just disappears, meaning that each price is just a function of the quantity of the same good. The price of good 1 is no longer depending on the quantity of good 2 when D is equal to 0. Okay, which is to say that the two goods are completely independent in the utility function of the consumer. Okay, so that's one extreme case. The other extreme case is when d is equal to b. In that case, you see that the weight of these two terms here, the term in Q1 and the term in Q2, the weight of these two terms is exactly the same, meaning that the price, for example, of good 1 is going to decrease in the same exact way when the quantity of U1 the quantity of good 1 increases or the quantity of good 2 increases. Okay, so in that case we say that the goods are homogeneous, they are just exactly the same. Any value of d between 0 and b indicates that the goods are not exactly independent nor homogeneous, they are somehow substitutes. Okay, and the larger d, the more substitutable the products are. Okay, now the next step is to go from the inverse demand functions to the demand functions. Okay, which is the expression of quantities demanded as a function of prices. Okay, so how do we do that? Well, it's a pure mathematical work that we need to do here. We just need to invert the system of inverse demands that we wrote on the previous slides. Okay, we can only do this if d is strictly less than b. If d is equal to b, then I show you below what we have. But when d is strictly less than b, this is what you obtain. This is the expression of the quantity demanded as a function of the two prices. Okay, the details are given on the next slide, and I advise you just to freeze the screen for how long, as long as you want, sorry, and you can check all the details that I have written on the next slide. Okay, so the only thing I want to stress here is that we are talking about substitutable goods. Okay, so no wonder that if the price of good 2 increases, you see that the quantity demanded of good 1 increases as well. Okay, so if the consumer sees tomatoes and cabbage as substitutable products, if the cabbage becomes more expensive, then the consumer is going to increase the consumption of tomatoes, right? Okay, so let me just say a few words about the specific case where d is equal to b. Remember, that means that the two products are exactly homogeneous, that they play exactly the same role in the mind of the consumer. It's as if, it's not a good example, but it's as if you were seeing tomatoes and cabbage as exactly the same vegetable. Okay, but in that case, from a mathematical point of view, you cannot invert the system of inverse demands. Why? You can see this here. If b is equal to d, this would be equal to 0, but you cannot divide by 0. Okay, and so that's just the technical explanation. But from an economic point of view, you can see that if two goods are seen as exactly the same, well, as soon as one becomes more expensive, well, no, the consumer is no longer willing to buy it. The consumer will exclusively buy the other good, the less expensive one. Okay, so with homogeneous goods, there is a discontinuity in the demand function, and this is what we have written here. Take good 1. Well, the quantity, and we'll start from the bottom, the quantity demanded is 0 if the price of good 1 is larger than the price of good 2. Okay, why would the consumer buy something at a high price if there is another good which is exactly the same and which is sold at a lower price? Okay. At the other extreme, if good 1 is less expensive than good 2, then it's going to have the whole demand. Okay, and the demand at price P1 is A minus P1 divided by B. Okay, so you see the inverse demand function is here. Now, there is an intermediary case where the price of the two goods would be exactly the same. Then the consumer is going to buy some fraction of good 1 and some fraction of good 2. The fraction here is written alpha 1. So it's going to split somehow between the two goods, which are seen as the same and priced the same as well. Okay, we'll go back to this demand function, which is discontinuous, when we briefly recall the Bertrand model next week. Right. So this is the slide I told you about, where I've put all the computations to go from the inverse demands to the demands, and you can just freeze the screen to read this at your own pace. Let me move to the next part. Okay, so that's the second example. So remember, the first example was an approach where we consider that all consumers can somehow be summarized by a representative consumer. Okay, it's as if all consumers were the same. Right, now in this second example we do the opposite assumption. We make the assumption that consumers are different. Okay, so they will behave differently for a given price. Some consumers would buy, others will not. Okay, but to have the demand coming from all the consumers, we'll have to add up the quantities demanded by all the consumers. Okay, and I just designed here a very simple example, which is, as you will see, another way to derive a demand which is linear. Okay, in the previous examples, the demands were linear. Okay, we'll have the same here, but using another approach to find them. Okay, so here is the example. Suppose you have 1,000 potential consumers, and they have each of them a unit demand for some product. What is a unit demand? As the words say, it means that the consumers are willing to buy 1 unit or 0, but they don't have any utility for a second or third or fourth unit. Okay, so think of buying a fridge, right? Well, you're going to buy 1 fridge and you're going to keep it for a number of years. Most of the people don't have a utility for a second fridge. Okay, so you buy or you don't, and your decision is very simple in a sense, because you are going to compare your willingness to pay for a fridge. We rewrite this V. You are going to compare this to the price set by the firms. Okay, and if this price is lower than your willingness to pay, you buy. If it's higher, you don't buy. Okay, so V is this maximum price. It's also called the pain point that a consumer is willing to pay for 1 unit of the product, and we assume that this V, this value, can be drawn is drawn from a uniform distribution, which is defined on the interval 0, 1. Okay, so it can. What does it mean, a uniform distribution? It means that this V can be any value between 0 and 1 with the same probability. Okay, and another way to say this is that there is an equal proportion of consumers for each value. Okay, so if I take a value V is equal to 0.6, okay, well, there is exactly the same proportion of consumers having this V equal to 0.6 as there are consumers with a V equal to, say, 0.4. Okay, it's also another way to say that is that, I mean, there is 60% of consumers with a value of V between 0 and 0.6, for example. Okay, now from there we can derive the demand function by aggregating the unit demands of all these consumers. Okay, so take some price P. As I said, the consumers have a very simple decision to make. They buy or they don't buy. Okay, and those who buy must have a sufficiently large value. They must have a willingness to pay V which is larger than the price. Otherwise, there is no point in buying if what you have to pay, the price, is larger than what you're willing to pay. Okay, so only those consumers with V larger than P buy. Now, how many of them are there? Well, that's here that our uniform distribution assumption is very makes things very easy. Well, the proportion of consumers with V larger than P is just equal to 1 minus P. Okay, all these consumers for V with V larger than P, this proportion is given by 1 minus P. Okay, I repeat, this comes from the fact that V is assumed to be drawn from a uniform distribution on this interval 0, 1. Okay, now this proportion has to be multiplied by the total number of consumers, so 1000 times 1 minus P gives you the total demand Q for a given price P, and this is a linear function. The slope is, the derivative here of P is a constant, right? And of course it's also a downward sloping demand function. right? So that's just an example to show that you can also build a linear demand function from the aggregation of the unit demands of a number of consumers who vary in their willingness to pay, right? Now, we want to move from the demand function to some measure of the welfare of the consumers. And I repeat here what I said before, that we take a partial equilibrium approach. We look at one market at a time, the market for vegetable in my example 1, or the market for fridges in my example 2. Okay, we know that consumers make many decisions, right? And they want to allocate their budget in the best possible way for them, which creates necessarily effects from one market to another. Okay, if I buy a fridge, I will have less money to spend on vegetables, for example. Okay, and so if the price of fridges increases, well, the demand for vegetables may decrease because of that. Well, although these effects exist, we ignore them here. Okay, we believe that they are not that important, and we really want to look at one market at a time, abstracting away these cross-market effects. Okay, if we do so, then a good approximation of the well-being of the consumers on one particular market is the consumer surplus. Okay, you may remember this concept. It's defined as the net benefit from being able to purchase a good or a service, and it's computed as the difference between the willingness to pay and the price actually paid. Okay, so in my previous example of a market for fridges, take one consumer who is willing to pay 0.7 for a fridge. Okay, you can multiply this by the unit that you want to have a price that has some meaning. But in my example, all values are taken between 0 and 1. So take a consumer who is willing to pay 0.7, okay, and think of the price that the consumer is to pay being equal to 0.5. Okay, so there is difference between the willingness to pay 0.7 and the actual price, which is 0.5. The difference of 0.2 is, for this consumer, the consumer surplus. This is a kind of benefit that consumer has of not having to pay the pain point, the highest price this consumer is willing to pay, and pay instead a lower price. Okay, so it's a kind of intuitive concept which we will use as such. There are problems that you may have heard about in microeconomics. We will abstract these problems away. There are problems about income effects, problems when you want to extend this concept to several consumers or to several goods. We just leave these problems aside. They're not that important for the kind of analysis that we will make, so we will just use the consumer surplus as a fair approximation of the well-being of the consumers on the market. Later we will talk about the firms, but you already know that if we want to measure the well-being of the firms, the intuitive measure is the profits of the firms. We will come back to that. Okay, so just to finish, let's compute the consumer surplus in all two examples. Okay, well, you see here example 1 is a bit more complex. I just walk you through the different steps. Again, take your time, freeze the screen if you want to read this at your own rhythm, and also redo the computations. But what is done here is that we started from the demand function, the utility function, sorry, we had above. Okay, and remember we computed the inverse demand functions, P1 as a function of the quantities, P2 as a function of the quantity. So what we do next is just replacing P1 by this value here, replacing P2 by this value here, and simplifying. Okay, so if you do this, the consumer surplus for this representative consumers, when she consumes a quantity Q1 of good 1 and a quantity Q2 of good 2, this boils down to this expression here, 1/2 of this bracket. Okay, it's even simpler when D is equal to B, so that's the case of homogeneous goods. Then the consumer surplus is proportional to the square of the total sum. or the sum of the total quantity. Sorry, I repeat, the consumer surplus is proportional to the square of the total quantity consumed, quantity of good 1 plus quantity of good 2. Okay, and in that case, if there is only a homogeneous product, you can represent it in a way that should be familiar to you. So you measure here on the horizontal axis the total quantity consumed. This is the price, and as we have homogeneous goods here, it's the same price for good 1 and good 2. And at some quantity Q bar, well, it will be sold at price P bar, and this triangle here in blue measures the consumer surplus. Okay, and you see here any vertical distance is the difference between what you read on the demand function, which is the willingness to pay of the consumer, the difference so between the willingness to pay of the consumer and the actual price. Okay, that corresponds to our definition of the consumer surplus. Okay, and that's it for today. You will see as an activity, I will ask you to compute the consumer surplus for example 2. You will find this is much easier than for example 1. Thank you and goodbye.